All right, we're talking about circular motion today, and let's get right into it. So, this is going to cover kind of a mixture of chapters, and it's going to begin with some stuff from chapter, I think it's 3, and then chapter 5, and then on into chapter 9 and 10. This is largely because I've kind of avoided talking about circular motion for a while, and now we're just going to kind of do it all at the same time. Now that we've really covered most of translational motion, which is like motion in a straight line, we like to talk about what happens when things travel in kind of curvy paths. All right, so let's go to full screen here, and let's get this to where I can see Discord. Okay, so let's start off by drawing a circle. Okay, so let's say I have an object that's traveling in a circular path. So for that, we need to know something about the center for its motion, which should be somewhere like right around here. We're going to need to know something about the radius of the motion. So let's label the radius here. I think we're going to call the radius of this circle capital R. Okay, so let's say we have an object that's moving in a circle. And what we're first going to talk about is called uniform circular motion. So for this, imagine we have let's say a ball on the end of a string that's traveling in a circle. And let's say it's like a horizontal circle. So we have somewhere here, we've got like a mass, m. And let's say that at a moment in time, it has a tangential velocity vector, which is pointing like this. Make it as tangent to the circle as I can. So this is going to be the velocity of the object. This velocity is going to be a type of tangential velocity. Okay, and again, let's say that this object is attached to it's a mass on a string or something that's going in a circle, or it could be like a planet, like the Earth orbiting the sun. It could be like the moon orbiting the Earth. Anything that's moving in a circular path like this right here. And at a moment in time, it has some tangential velocity. And first of all, we're just going to look at what we'd like to figure out is what is the acceleration of this object, okay? So if it starts off at this location and after some time has passed, it moves over to like here, and it's traveling on this circle. And once it gets to this location, it's going to have a velocity vector that's going to point down like this. And we're going to say that because it's uniform circular motion, that means that these velocities are going to be the same as each other in terms of magnitude, but their direction is going to change. So that means that if the velocity is pointing this way at one point, and then it's pointing down this way at another point for this object, that the direction has changed, but the speed has not changed. But when you have the direction change, that can create an acceleration, right? And what we'd like to argue here, or prove, is that there's going to be an acceleration on an object that travels in a circle that points toward the center of the motion. That's what we'd like to prove. So to do that, we're going to draw some position vectors on here. We use black. So this will be the initial position vector. I'm going to label this as R initial. Let's use just R naught actually. And this will be R final. Maybe we could just call it R, but I'll call it R final. Maybe to avoid using subscripts, I'm just going to label the initial vector as R naught, and the second vector, I'm just going to call that R. So you can think of this vector right here represents the initial position of the object, and then this vector R represents the position of the object at some later point in time, relative to the center of the circle. Okay. Next thing we have to put on here is a vector to represent the change in position, which would point from the initial vector to the final vector right here, like that. So I'm going to label that vector to be the change in r, or the change in position. And what I would argue is from this picture, you can prove that delta r is equal to r minus r naught. See if you can figure that out by looking at the vectors. Does that seem reasonable to you all? And one way you can see it is that r initial plus delta r ends up being equal to r because they're added like tip to tail and stuff. Okay. Now let's add one other thing in here. We're going to need a time. So let's say that the time that it takes to go between these two positions is delta t. I don't know where to write on there, but we'll just put somewhere in here delta t. I'll just say that this is the time from r initial to r. So delta t is going to represent the time. And again, our goal with this is the speed is constant, but the direction isn't, right? And so our goal is basically to find what is the acceleration of this system. That's what we're kind of going with all of this. Okay, for an object that moves with a constant velocity in the circle, what's the acceleration going to be? So now that we have a time and we have some velocities, we know that we can define acceleration as being equal to basically the change in the velocity divided by the change in time, right? That's ultimately going to be what we need to write down for the acceleration, right? All right. Now, in order to do that, we're going to employ kind of a trick from geometry. So if I call this angle right here theta, the angle between r initial and r final, this angle right here, then what I can do is I can say that if I were to take my initial velocity vector right here, and if I were to put it right here, I would argue that this angle right here is also going to be equal to theta. And let's actually label these velocity vectors in the same way. So let's call this initial velocity vector v initial. Whoops. How come my undo button's not working today? I don't understand. So we do v initial right here, and we'll call this vector v final. So when I shift v initial over to here, so this is now v initial. Maybe if I labeled it v final on the other side, it'll be a little easier to see what's going on here. Okay, so we got v initial and v final, right? And I don't know how accurately it shows up on the picture that I drew, but if this is a right angle right here, and it has to be because a line drawn from the center to the edge of the circle, if I have a tangential velocity vector, there's going to be a right angle between the radius and that velocity vector. Same thing down here. So if you think about it, then this radius vector, when it turns in this direction down to r, that velocity vector is going to tilt through the exact same angle. So let's say that this angle right here is also going to be theta. Can you all see that? It's like, I want to kind of draw a sketch over here. We start off with a vector this way and this way, right? And let's see, this is r naught, and this is v naught. Sorry, that r kind of looks like a v. This is r initial, and this is v initial. They're attached at a right angle like this right here, right? So if I tilt one of them to here, to r final, and the angle that it rotates through here is equal to theta, then this v initial has to rotate through the exact same angle, right? Because it maintains that right angle nature, right? Does that make sense to you all? Yeah, so it's like if it's an L and it continues to be an L, then if this goes through an angle theta, then the v initial and the v final also have to angle theta between the two of them, right? Okay, I don't know how helpful that is, so I'll put that over here. This would be your v final. So we're basically taking out a velocity vector, we're shifting it down here and saying you get the same angle. Okay. So now what we can do is we can say, well, if we take another vector and we draw it from v initial to v final like this, I'll fix it, but this here. Now I'm going to call this vector delta v. Why do I care about that? Well, ultimately we're trying to figure out the whole goal of this is to find acceleration, right? And if I can say something about this delta v vector, I can find acceleration. And why is this delta v? Well, it goes from v initial to v final, which means that just like what I wrote up here for delta r, I can also write that delta v is going to be equal to v final minus v initial. For exactly the same reason. V initial plus delta v is equal to v final. So it satisfies that relationship right there. Okay. Now, the next thing that we can do is we can start to say that we have a special type of triangle here where, well, let's look at the black triangle first, the one made of the radii. What type of triangle is this going to be? It's not a right triangle. What type of triangle is this? It's an isosceles triangle, that's right. So r and r initial have the same magnitude. They're not the same vector, but they have the same magnitude of r. So the magnitude, oh, why is this not working anymore? That's so annoying. I used to be able to push just that button and it would automatically erase the last thing I did. It's not working anymore today for some reason. I wonder if, that was it. I guess my control key was stuck down. I don't know why that happens so frequently and only with one node, but it does. So what I was going to write down is that if I write the magnitude of r, I can say that that's equal to the magnitude of r initial, which is equal to the radius of the circle, right? And we can do the same thing for the velocity vectors because the speed is constant, which means for our velocity vectors, we can write down that v initial magnitude is equal to v final magnitude, which is going to be equal to the speed, which I'm just going to call v. Okay. So that's an isosceles triangle in black there. And the red triangle is also isosceles, right? So both triangles are isosceles. And they have the same angle. So what does that mean about these two triangles? They're both isosceles and they both have the same angle right here.
They're perpendicular?
No. Similar, right? So that means that these triangles are similar triangles. I don't know if everybody remembers that from your geometry class or if you were paying attention in your geometry class, but similar triangles are triangles that have the same proportions, but might not have the same size. So a really simple example of this is I'm going to use these two as an example. So we have like our triangle that involves r, which is like shaped kind of like this. Kind of like that. So that's our r triangle. And probably the easiest way to think about this is if the triangle here has an upper angle theta, and this side is r and r, right? If I draw a line that's parallel to the bottom, that goes from here to here, but I make it parallel to the base, like that. And then I tell you that, let's see, this side from here to here is v and v, okay? So r goes all the way, and then v is just the shorter piece, so r goes all the way down to here. And then v is just this piece right here, just this distance here. Remember what the other side was, right? This side right here was delta v. And this side over here was delta r. Those are our names for these things, right? Then, when you have similar... Okay, now that I draw this like this is basically what's happening here. So similar triangles, right? The triangle with the velocities is similar with the triangle with the radii, right? And what can I do with similar triangles? What can you use them to do? How can I relate the sides of the smaller triangle to the bigger triangle? No, we're not going to find angles.
Is there like a constant to multiply them by?
No. Maybe, but what do you mean by that?
Like if we multiply a smaller one, is the smaller one triangle by a constant, we can find the length of the sides.
Kind of. We can make like ratios. Is that what you're thinking of?
Yeah.
Yeah. What Chris is saying is kind of on the right track. We're going to make a ratio, basically. So our ratio in this case is going to be that we're going to take the ratio of like one side here, v, to delta v, and it should have the same ratio as r to delta r. That's what you can do with similar triangles. Basically, they're proportional to each other, which means that if I take the ratio... I'll tell you a simple one. If I take the ratio of this side to this side, what's the ratio? If I take the ratio of v to v, what's the ratio? You can just cue your mics and say. You don't have to type. It's okay. You can type if you want to, but... What's the ratio of v to v? It's 1 to 1, right? And that's the same ratio as r to r. Now that one's really simplistic, but it's true, right? V to v is the same as r to r, 1 to 1. Also, it would also be true that the ratio of v divided by delta v would be the same as the ratio as r divided by delta r, right? Does this kind of ring a bell? Do you all remember doing any of this in geometry, or has it just been so long that you don't remember anything? Which I would understand, but...
This kind of rings a bell.
It rings a bell. Okay, so you did this at one point in time, and you all just forgot all of it, and that's fine. But now we're using it again today, as often happens in mathematics. You learn something one day in mathematics. Stop talking, Chase. You're getting some echo.
Oh, sorry.
Yeah, it happens a lot in mathematics, right? That you learn something one day and then you forget about it, and then it shows up later on in other classes. It's just pretty normal. Okay, so similar triangles, in case you don't remember, that's kind of a rundown of how it works. So in our picture, we're going to do the same thing, but I think we're going to try to use... we're still going to kind of do the same thing, right? So let's see, what do we want to do? On the left-hand side, I'm going to write delta r, the ratio of that to big R, or... I'll write it as the magnitude of our initial. We'll do it like that. We'll do the magnitude of delta r up here. And then on the right-hand side, we'll do the magnitude of delta v divided by v initial. So that's pretty similar to what I wrote over here, right? Except I'm not skipping a step. So this ratio should be good. And... now let's plug in what these things are. So for delta r, I'm just going to leave it as just delta r magnitude. For r initial, I'm going to write that as capital R, because that's what we said that was equal to. And then delta v, we'll just write as just delta v. And then on the bottom here, we're going to have a v. The next thing we're going to do is we are going to divide the entire thing by 1 over delta t. So on both sides, we're going to put 1 over delta t here. And on this side, we're going to put 1 over delta t. I'm also going to take this velocity and move it to the left-hand side. So what we're going to get is, on the left-hand side, we'll have v over big R times delta r divided by delta t. On the right-hand side, we'll have delta v over delta t. I'm keeping these magnitudes on here. Move that up a little bit. Remember that delta t is the time interval that it takes to go from this initial position to this final position here. Okay, do those steps make sense? Does anyone have any questions? Okay, now let's look through and think about what these things are. So what is delta r over delta t? Yep, this is the same thing as the velocity of the object, the same velocity that's here. So this can be written as v over r times the velocity. And in case you don't remember that, this is change in position divided by change in time, right? Now, this would be average velocity, but we can do one other thing here. Just to kind of skip a step. Let's take the limit as delta t approaches 0, which will make it instead of just being average velocity, if we take the limit as delta t goes to 0, this will become the instantaneous velocity v. And then what's the right-hand side going to become? Delta v over delta t. That's the change in velocity divided by change in time, which is acceleration. That's right. So what we get as our answer, I'll just put the answer right here, is that our acceleration is equal to velocity times velocity, so that's velocity squared, divided by the radius of the path. And we call this kind of acceleration centripetal acceleration, A sub c, so that stands for centripetal. Not centrifugal, which has an F in it, but centripetal acceleration. And it's sometimes referred to as, I'll just put another name in a different color here, radial acceleration, because it points along the radial direction. And we can see that in our picture here, kind of. So our picture is it's not exactly the same thing as what we've written here because we've taken the limit as delta t goes to 0. So if delta t goes to 0, these two vectors are going to get closer to each other, right? Like basically as delta t goes to 0, these two vectors are going to be like this, you know? They're going to be a lot closer to each other. I love that I can't just do this. It's just so great. Okay. But what's the direction of the velocity? Or the acceleration? Well, the direction of acceleration, A, has to be the same thing as the direction of the change in velocity, right? So, what direction is the change in velocity vector? Well, it kind of points this way. And to say that it points that way, it's kind of pointing off to the left right here. But again, if you imagine that these two vectors got closer and closer and closer to each other, v initial and v final and r initial and r final, then what you'd find out is that this velocity vector ends up pointing, the change in velocity vector here ends up pointing directly towards the center of the circle like this. And you can especially see it because if I take my delta v vector here and I put it exactly halfway in between these two, here, let me copy paste it. Let's copy and paste it. Click copy paste. All right. So here, if I put it right in the center of this little triangle we created, and this isn't going to be perfect because I don't know how much of an actual, whatever. It pretty much points directly to the center of the circle, right? Would you all agree with that? Pretty much is pointing right at the center of the circle. Okay. So that's why we say it's like a radial acceleration, and the word centripetal means center seeking. So it points towards the center. That's what that word means. Okay, so centripetal acceleration. When you have an object that moves with uniform circular motion where the speed is constant, then you're going to get a centripetal acceleration that looks like this right here. And what we'll be doing for the rest of class is kind of using that type of acceleration to analyze forces acting on objects that move in circles. And figuring out, what are the forces that actually produce the centripetal acceleration. That's what we're going to do today. Anyone have any questions? What if the speed's not constant? So if it's non-uniform circular motion? Well, we'll talk about problems like that too. And we're still going to be able to use this idea even in those type of problems. Okay? There's just going to be a combination of linear acceleration combined with centripetal acceleration. I can give you an example of both of those. trying to decide if it's too soon to do this example, but I think it's okay. So let's look at what is the easiest. Oh, I think the easiest example problem we could do would probably be this one to start with, I think. And then we'll go from there. The simplest answer to your question in summary is that even when an object has a non-constant speed, if it's non-uniform circular motion, at a point in the motion, this is still going to be the acceleration. Does that make sense? So, yeah, let me just go ahead and give you an example to answer your question in a better way. So think about the following scenario. Suppose that I have a hill, and the hill is shaped kind of like this, okay? It's kind of like a hill that's shaped somewhat like the like a hemisphere or so, or like a quarter of a circle or something like that, right? And let's just say that I have a box that's sliding down this hill. So it slides from here down to here and down to there like that, okay? So as the object is sliding down, it is going to be accelerating in two different ways, okay? In one way, and let's just look at the object when it gets to this point right here. In one way, it's going to have an acceleration that's going to be pointing down the ramp like this. I really need to use vectors for this, or it's going to end up looking bad. So it's going to have an acceleration along the ramp that's going to go this way. And we call that the tangential acceleration. So I'll call it a tan, which is basically the... Let me just write over here. That's tangential acceleration. That's the direction of the acceleration along the path. And in this case, that tangential acceleration would be coming from where? If I just have a box that's like sliding along a surface like this, what would be producing that tangential acceleration? Gravity. Exactly. Gravity. Same thing up here, right? When the object is at the top right here, it would have a tangential acceleration. It would just be pointing kind of down like this. And that would also be produced by gravity. In fact, if it was a completely shear surface, like if you're sliding down a surface and it's completely straight up and down, then your tangential acceleration would be exactly equal to gravity. But as you move down this way, your tangential acceleration is going to be something like g times the sine of the angle made between the plane and the surface of the Earth, right? So this type of acceleration we've already talked about because it comes from the acceleration due to gravity, right? But in addition to that, if you look at the direction the object's moving, at one point it's moving down, and then it's moving kind of down to the left, down to the right, sorry. And then eventually it would get to a point where it would just be moving kind of flat along the surface down here, right? And let's add something to this picture. Let's actually allow it to curve up like this, so that eventually it'll get to here. Oops. Eventually it's going to be like right here. So this object, it slides down this way, and then it slides up to here. What would the direction of the tangential acceleration vector be when it gets to this point? When it gets to this higher point right here, what direction is the tangential acceleration point then? Backwards, right? Yeah. So if we use a vector, it's going to kind of point back like that, and that's going to be our tangential acceleration vector. Okay. Now, at all points in the motion here, maybe not so much here, but at all points in the motion here and here and here, there's another velocity vector, there's another acceleration vector, and that would be what we call a radial acceleration vector, or centripetal acceleration vector, whatever you want to call it. Your book likes to use radial acceleration. I always used centripetal when I was learning this stuff, but yeah. So there's also an acceleration vector that points like this. So we call this one the radial acceleration, a radial. And this one is always going to be perpendicular to the tangential acceleration. That means it's also always perpendicular to the surface itself. Okay? And this radial acceleration is the same thing as this, centripetal acceleration. Which means that if I knew the velocity of this object, right? So for example, if this object had a velocity here that we called v1, and if it had a velocity here that we called v2, for example, then we could say that this radial acceleration vector, its magnitude at least, would be equal to v squared divided by the radius of the motion. Well, what would the radius be? So the radius would have to be like, imagine that I draw a circle here at this point. I draw a circle that kind of just touches my surface. Then the radius of that circle would be the radius that would show up here, okay? And when the object is down at the bottom right here, let's say that this surface is completely flat at the bottom right here. So let's talk about this point right here. Let me say one other thing over here. Tangential acceleration vector has the effect of changing the speed of the object. We'll just say it changes speed. While the radial acceleration vector, or the centripetal acceleration, changes the direction of the velocity. Okay. So let's look at this very bottom point right here. What's the direction of the radial acceleration vector when it's at the very bottom down here? It's towards the center, which is straight up. Yep, exactly. Oh, I wanted to use green again. Whoops. So at this location, it would be pointing... Oh, okay, click this, like this. Straight up. So that would be the direction of the radial acceleration. Now, the length of these vectors is going to be proportional to the speed of the object. So, in reality, the place where the object's going to have the greatest speed is right down here at the bottom, right? So maybe I'd make that one the biggest. Okay. And then if these two are about the same height, they'd be about the same, so that's reasonable. What about the tangential acceleration when it's at the very bottom here? And again, we're going to assume this is a flat surface right here. At the very bottom. It's just flat only at the very, very, very bottom. What would be going on with the tangential acceleration at the very bottom? Is it forward or is it back? Something else? No, not down. It's 0. That's right, Joanne. So at the bottom right here, a tan is equal to 0. Because again, going back to what it is, it changes the speed of the object. So in the case of an object that's traveling along a curved surface like this, it's gravity, right? Gravity is the thing that actually produces this tangential acceleration vector. And when the object gets down to the flat surface at the bottom, it has no tangential acceleration. That is to say, gravity isn't doing anything, basically, right? Now, all these same topics can be applied to, like, a ball on a string if you want to. And maybe it's an even simpler idea. So let's just to kind of, like, drive this idea home, let's draw an actual circle in here. I'm gonna make it bigger. Make it actually a circle. Oops, too much. Okay, let me move this one down a little bit here. So let's apply the same concept that we just talked about to like a pendulum. Okay, pendulum might be a little bit easier to understand. I don't know, maybe not. All right, so we're gonna erase most of this circle, and let's say we'll go down to like right about there. Okay, so let's say that I have, you know, what I should have done is I should have actually marked off where the center is, but we can find the center by doing this. As long as I make that a right angle, the center should be somewhere like right there. Okay, so doesn't look like the center. That's okay, I guess. Okay, so let's say that I have a mass on the end of a string right here. So this is a mass right here. And it's going to swing from there down to here and then back up to here again, okay? So we'll draw another little string right here. And let's say that the mass, so let's say the length of my string right here is L. And it's suspended from some point right here. So here's the ceiling. And I have a mass and it's suspended like this. And let's say that we basically release this from rest. Okay. Maybe we're going to probably draw some other points in here too, actually, because I think that's probably relevant. So let's draw a couple other points in here. All right, so there's our mass and it's sliding along like this. Okay, so when the mass starts to move, what's the direction of the tangential acceleration at the beginning? So it's released from rest and it's going to swing all the way over to here and it's going to be at rest again right here as well. Is that the same with the video on YouTube, Professor? Which one are you talking about? To the right, it's kind of down and to the right. Yeah, kind of similar. Yes, similar. Same kind of setup, right? What I'm talking about here is basically like you take an object, which is like a ball on the end of a string, or it could be like a pencil or something like that. You pull it to the left like this right here, and then we're just going to let it go. That's what we're describing. You can do this with like, anything. I don't have any like strings or anything like in my house, but take a ball on the end of a string, hang it from a point, and then just pull it to the left and let go, and it'll slide. Okay. Same direction as the path. That is right. Okay, so the radial acceleration vector here would basically point in the same direction as the path. So we're going to keep using vectors. It's kind of time-consuming, but it makes the pictures look better. So the radial acceleration at this point would be going this way. And I'm going to go through at every point, and we're just going to say at every point where the object is I'm so sorry. This is going to be the tangential acceleration vector. So that's what this purple thing is going to represent. I don't want to keep writing A10 every single time. So here's the question. Which one of these should be bigger? Should I have a bigger tangential acceleration at this location or at this location? Where's the acceleration going to be the biggest? The first one, right? Okay, so let's make the first one a little bit bigger than the second one. We'll make this one just a little bit smaller. And then what about the tangential acceleration when it gets to the middle right here? It's going to be 0 again, right? Okay. And then when it gets to this point right here, it's going to be slowing down, right? So now the tangential acceleration vector has to point back like this. And finally, when it gets back to the top right here, it's not moving, but it still has a tangential acceleration vector, and this one should probably be about as big as this first one right here. Okay. So every one of those represents a tan. Again, a tan is the tangential acceleration vector. Okay. And it's going to have a different velocity at every point too, right? For example, what's the velocity at this point going to be? The velocity at this point is going to be the place where it has the highest velocity, the highest, right? Joanne says that's right. Vmax says, hey, yeah, both of those are correct. So we're going to say at this point the velocity is at its maximum, right? So we know it starts off with a velocity of 0, it finishes with a velocity of 0, and then it has a velocity kind of in between here in the middle, and when it gets to right at the center at the bottom, it's going to have a maximum velocity. Okay, so we'll use those to write down what we need to write down. Now, at first, the radial acceleration, and just to remind you, radial acceleration is equal to velocity squared divided by radius, right? In our case, that's going to be the velocity squared divided by the length of this string right here, right? So let's start drawing some radial acceleration vectors. Okay. So if the velocity is 0 right here, what's the radial acceleration going to be? It's also 0, right? Because like that's what the equation says basically, right? Okay. So no radial acceleration there. Although technically it would feel a force. It's just the value would be 0. Okay, when it gets to this point right here, its radial acceleration vector is going to point basically directly along, well, the radius or the chord. So that's the direction of the radial acceleration at that point. We'll make it kind of short like this. So here's the radial acceleration here. And then when it gets down to the bottom, it's also going to have a radial acceleration vector there. It's going to point straight up like this. This is going to have to be the largest value for the radial acceleration, because that's the place where the velocity is the maximum, and you take velocity squared divided by the radius. And then when it gets back to, oops, right here, again, its radial acceleration vector is going to point along the radius, and it's going to be a little bit smaller. So there we go. Just kind of looking at how the acceleration changes without talking specifically about forces. We could analyze everything that's happening here in terms of forces if we want to, but we just want to kind of talk about what's happening with the accelerations. Okay. So does anyone have any questions about these ideas, about what tangential acceleration is, what radial acceleration is, why it's equal to v squared over r? You know, any questions at all? All right. So this problem is actually kind of tricky. Let's start with this one, because this is going to be a kind of an important result that will show up in a few different problems. Let's start with this one right here, example 10. This is something you can try at home if you really want to. And I would show you a demo of this if we were in the classroom, but we're not, so. Okay. So if you have a bucket at home that you can like fill with water, you can test this out right here. Okay. So this is basically what the problem is saying. It says a cup filled with water is making a circular motion of radius r. Find the critical speed at the top such that no water is lost. Okay, we'll draw that problem, but I want to show you something that you can kind of like try for yourself at home. So let's say that you take a bucket, okay? So a bucket is like, you know, shaped kind of like this. And it's got some water in it. Down here. And usually buckets have handles, right? So it's usually like a handle like this right here. So take a bucket and just hold it with your hand at this location right here, right? Maybe some of you have tried this before. You can take this bucket and you can basically swing it around in a circle like this, so that at one point in time, I'll draw a person inside of here. So you're going to basically hold this with your hand, and you're just going to swing it over your head and around like this, basically, right? And what will happen is that when the bucket gets to the top, let's see, can I just flip this bucket drawing upside down? Is there a way to do that? I think there is. I think there's a way to just flip it. So when the bucket gets to be upside down right here, so you're holding it there, so it's going to be like right here, right? There we go. So you swing your arm around in a circle like this. So at some point your arm is going to be up here, and then it's down here. So you're basically just going around in a circle like this right here. You can do this in such a way that basically none of the water will fall out at the top. Have any of you ever tried something like this before? All right, so this is something you have some experience with, right? The same can be true, like, you know, you could just swing the bucket back and forth and you kind of notice that the water doesn't really fall out as long as you do that. Okay, now, of course, if you were swinging this bucket around like this and you swung it up to the top and you just didn't have quite enough speed, well, then the bucket would kind of start to fall down, right? So you have to swing it fast enough so that it keeps going in a circle, right? Or else the bucket's basically just going to fall down, right? So that's what we want to analyze. The question is basically, how fast do you need to rotate it when it's at the top, the critical speed, so that none of the water ends up falling out, okay? So that's what we want to figure out. Because how fast do you need to rotate it such that none of the water falls out, okay? So in order to analyze that, what we need to do is we need to say some things about what's going on here. So let's define the velocity at the top to be, I guess we'll just call it v top. Okay. And we want to figure out what that needs to be, or specifically the critical speed. This means basically going to mean the minimum speed that we can have at the top so that no water is lost. That's what we want to figure out. What is the minimum speed or the critical speed? Okay. So in order to do this, what we want to do is basically think of all of the water as just kind of like one object, okay? In fact, it doesn't have to be water in the bucket. It could be just a rock or something like that. Because it's the same question. Suppose I put a rock in the bottom of the bucket and I swing it around. The rock could easily stay in the bucket as long as we rotate it fast enough, right? So whether it's a rock or water doesn't really matter. We're going to analyze the forces on the water is what we're going to do, okay? Now we haven't really talked about fluids in this class, but I'm just gonna say that if that's confusing, just replace the water with a rock. So that means that we're basically just going to draw forces acting on this, just like we normally do. So what kind of forces would the water experience here when it's at the top? Gravity, that's a weight, right? So it's going to have some weight that's going to go this way. What other forces is it going to feel? A normal force? What direction is the normal force from the bucket going to point? Down, yep. So there's also going to be a normal force that points down like this. What other forces would it feel? Maybe some air resistance, yeah. We're not going to worry too much about that, but certainly there would be some air resistance as well. So mostly just these two forces here, right? So if I want to draw a free body diagram off here to the left, then I'm basically going to have normal force pointing down, weight pointing down, and then what's the direction of the acceleration when it's at this point? Is it accelerating upwards, left, down? Okay, I see a few people saying left. Joanne's saying down. Joanne's right. The direction of the acceleration at this point is down toward the center. This is the direction of the acceleration. And it's also a radial acceleration, right? Now, again, if that doesn't immediately make sense to you, and you think that it's accelerating to the left, think about this picture right here. It's exactly the same idea, it's just upside down. So I have a ball, it's attached to a string. It accelerates down to here and then down to here, but right when it gets to the very bottom right here, notice that all of its acceleration is pointing straight up. Because gravity cannot accelerate it left or right, right? Think about the same thing right here. Gravity cannot make the water go left, right? Gravity cannot make the water go right. Because it only points straight down. So there's no tangential acceleration, and it's not accelerating to the left. All of the acceleration is downwards. Okay. So that's our scenario. Normal force, weight, the radial acceleration pointing that way. So now what we could say is that if we define this to be the positive r direction, let's say, the radial direction, right? That if I sum up all the forces acting in the radial direction, that should be equal to the mass of the object times its acceleration in the radial direction. The forces in the radial direction. So this is just using Newton's second law to apply to, it's accelerating, right? So Newton's laws still apply. So net force in the radial direction is basically N plus W. And that's equal to M times A radial. Remember that, like as I said above, the radial acceleration is going to be equal to the velocity of the object squared, divided by the radius of the path, which I haven't defined here, but let's call our circle to have a radius of r. Like that. Okay, now our goal here is to figure out the minimum speed, right? And in order to do that, what we can do is we can kind of rearrange this equation. So I can multiply r over m times n plus w. And then that should be equal to the velocity squared, which we can square root both sides. And we get that this is going to be our velocity at the top. We can call this v top if we want to. Now we need to minimize this. We need to make this as small as possible. but what can we control? So let's assume that the radius is a fixed value, that we're not going to change the radius because it says of radius r, so we can't really alter that. We can't really change the mass of the water either. That's kind of fixed, not without pouring water out of the bucket. But it doesn't really matter how much water is in the bucket. The speed should have nothing to do with how much water is actually in the bucket. The amount of water in the bucket is just going to determine how hard it is for you physically to keep rotating it around before your arm gets tired, right? How heavy it is, basically, right? And the weight of the water that's in the bucket, we really can't control that either, right? It's just like the mass, like whatever mass we have, that's going to determine the weight, right? So there's only one variable in here that we can actually alter, and that's the normal force. So we have to think, we want to find minimum speed, so we want to make the thing on the right-hand side as small as possible. And we know that the only thing that can even change in any way is the normal force, right? So we can kind of use this idea to come up with a reason as to why, or sorry, we can state in a different way what critical speed means. Okay. So the question is, we don't want to lose any water, right? It needs to go around in a circle, and we know that the normal force is going to have something to do with it, right? So what do you think would be the condition on this normal force that would produce the minimum speed? N equal to 0. That's right. That's right. I mean, the smallest, this number can't become negative, right? The normal force can never become negative. Think about what it is in case you don't remember. The normal force is the force of the bucket on the water, right? So there's no way that the force of the bucket on the water could suddenly start pointing this way, right? That's not possible. The only way that would happen is if the bucket had some property that it was sucking water into it, like, I don't know, if it was a vacuum or something like that. I don't know. Or if you replace the water with iron and you put a magnet on the bottom of the bucket. That could change the normal force because you'd add a magnetic force or something like that. But anyway, so this is the condition, n equal to 0, that produces the minimum speed, right? So we'll just make n equal to 0. And what does that physically mean? We'll talk about that here in a second, okay? What does it mean that the normal force is 0? Maybe you could write in the chat as I'm doing this. What does that mean that the normal force has become 0 now? Weight is m times g. What does it mean that the normal force is 0 physically? What's going on inside of that bucket, if that's the case? There's no contact force between the water and the bucket. Yeah. So what does that kind of mean about the water? It's like, it's almost as if the water is about to fall out of the bucket, right? I mean, that's what that means, right? So if I take this is empty, right? I think, okay. Suppose this cup was full of water, right? And the water in the bottom would be feeling a force from the bottom, right? There'd be a normal force on the bottom, right? What happens when you turn an object upside down like this? Well, if there was water in there, it would no longer feel a normal force, right? The water would just fall to the bottom. So it's the same kind of concept, right? Basically, the idea is that you want to make it so that when the bucket gets to the top, the water is almost about to fall out. For just a moment, it's as if the water is about to start to fall out of the bucket, but then as you tilt it a little bit to the left, yeah, or that's another way of putting it somewhere, yeah, the water leaves the base of the bucket for like a millisecond or two, and then as soon as the bucket is tilted by just a little bit, now the kind of the inner surface, I don't know if I can point to it, but the inner surface here can now support the weight of the water, right, as it tilts, until you get down to this point right here, where there's really no chance when the water's at the bottom of the water falling out of the bucket, right? Yeah. Let me give you another example that's basically the same concept. So you could do this. You could do the same experiment without a bucket and water if you're worried about like making a mess or whatever. Although there's really not much of a. It's not hard. you have a natural intuition when you're trying to do something like this for how hard you need to swing it before the water will fall out of the bucket. Because if you don't swing it hard enough, then the bucket won't actually make it above your head, right? Like if I'm just sitting here and like swinging it kind of slowly, the water's not actually going to make it around. So you have to swing it hard enough to go around, and you know pretty well that as you're swinging it, you can kind of feel this force that you're pulling inwards, right? That's where that radial acceleration is coming from. So this concept is going to show up in a lot of problems that you're going to have, which is why we're going to start with it here. Why are we starting with this? This minimum velocity at the top is going to show up in all kinds of problems, okay? So this is one example, and the minimum velocity you need is always going to be equal to this. Square root of the radius times gravity, okay? Let me show you two other places where this is going to show up, okay? So we could replace the same setup right here. We could just replace it with a ball and a string. So we could basically be swinging a ball around in a circle like this, and we could ask, okay, what is the minimum velocity that the ball needs at the top so that it actually completes the circle, for example, right? And the answer is going to be square root RG. But the condition is going to be a little different. So if I'm swinging a ball on a string and I want to make sure that the ball actually makes it around the circle, then if I analyze the forces on the ball at the top right here, what would the forces be? So this is kind of like our pendulum. Weight, and then what else? Well, weight and gravity are the same thing. So what else? Tension. Yep. So you'd also have tension going down like this, right? So what's the condition with the bucket was that the normal force became 0. What's the condition here going to be for the ball just to make it around for the minimum speed? The tension's going to go to 0, right? Yeah, exactly. So it's the same idea. It's just this force, which if you think about it, this is the radial force, right? This is the force that is pointing along the radial direction, just like the normal force in this case was. Okay, so that's another example of where it's going to show up. Okay, and then the final example, and you're going to see multiple problems like this, both in the lab manual as well as in your book. These are kind of classic physics problems. So a really common problem, and maybe we'll solve this later today or next week, would be, suppose I have a block of mass m, and I'm gonna like let it slide along a track. Maybe it's a frictionless track, and there's a loop-the-loop right here, just like to show up in roller coasters. So you could ask the question, how high do I need to drop this from? How high do I need to drop this block from such that it can complete the track like this? Okay, this is the kind of thing that if you were designing like a roller coaster and the roller coaster had a loop-the-loop in it, you want to make sure that when your passengers are riding around that loop-de-loop that they don't fall off the track at the top, right? So what would be the condition on these riders so that they could get to this point right here? And the idea is that this is like a circular path of radius r. How high do I need to start them from so that they can get up to the top right here? And the answer is going to be related to this idea right here, because we know that when this person gets to the top right here, the minimum speed they need at the top is equal to, that's not the right answer, Summer. It has to be a little bit higher than that. The minimum speed that they have at the top right here is going to be equal to the square root of r times g. Your answer, Summer, would be, suppose, okay, I'm gonna show you what the difference between the question that I'm asking here and the question that you're answering. Suppose that I ask this question. Suppose I have a level surface right here, and then I have a slanted thing like this, and maybe something like this right here, okay. So if I release an object here and give it some kind of a push, then it can slide down to here and it can come back up to here as long as these heights are different from each other, right? Like let's say these heights are pretty close to each other. Call it h initial and h final or something like that. I know that if I push this object, if h initial is bigger than h final, then it can get up to this point right here, okay? But the picture over here on the left is slightly different, okay? Because this object, not only does it need to be able to get up to this elevation right here, but it also still has to have some speed left over. Does that make sense, Summer? So the actual answer is going to be like 2.5 r, I think. Like 2.5 r. We're going to calculate this later on, right? But can you see how the concept is the same as what's going on with the bucket and with the rope? the idea is that in order for this object to actually complete this loop-de-loop, it has to have this minimum speed at the top, or else it'll fall off the track somewhere before that. And of course, we have demos of all these things that I have at the school, and I can't show you that. Anyway. So that's what this kind of stuff is going to be used for, the minimum speed stuff, right? Okay, so I introduced to you all the idea of centripetal acceleration. We talked about how it's different from tangential acceleration. Tangential acceleration, in a very real way, is what we have been talking about up until now. The acceleration of objects along surfaces or along inclined planes or along curved paths. We've been talking about this. This type of acceleration we've been talking about all semester long. So the radial acceleration is a new type of acceleration. It always points perpendicular to the path. It has this value. And, we did one example here, but we're going to spend the rest of class looking at just different applications and examples of this centripetal acceleration, right? Okay, this is a good time to take a break. We're going to when we come back, this is the problem we're going to look at.